All right, so welcome everybody. This is a Flow seminar where Flow stands for Federated Learning One Word Seminar that was created to provide a global online forum for the dissemination of latest scientific research results in all aspects of federated learning. Today, it's my great pleasure to introduce you our speaker, Salman Toor, who is an associate professor at Uppsala University and he's an expert in e-infrastructures, distributed computing, and federated learning. And he holds his PhD in scientific computing, and he's also CTO and co-founder of Scale-Up Systems. And today he's going to tell us more about secure and scalable distributed systems. Thank you so much for accepting to give a talk at Flow, and floor is yours.
Thank you very much, Samuel. Yes. So what I will cover today is more like a journey where I would like to highlight where our initial focus was and when this cybersecurity angle together with FL started to become more interesting for us. And also I will present the recent article that we have recently published together with me. Osama Zafar is also joining us. He's my PhD student, and the article is mainly his contribution to the area. Okay, let's start. So first of all, a bit from the environment. We are from Uppsala University, and we are running this scientific machine learning lab research group here, where we have 3 associate professors in the group, 1 postdoc, and 10 PhD students. And the areas that we cover is more towards all the way from theoretical side of optimization. Then my focus, that is mainly from Prashant Singh's area. And then my main focus is towards distributed infrastructures and federated machine learning. So on the website, you can see different publications and initiatives and projects that currently we are running there. So I think when it comes to the federated machine learning, I think most of us are very familiar of that. It's like a decentralized way of model training where the data never leaves the client's premises. Very nice. Mostly people talk about privacy preserving settings and highlight this as a privacy preserving solution. But when we see the same federated machine learning approach towards from the angle of communication efficiency, that is also very well highlighted in the literature. So for that, if we say that, okay, overall the model size is 10 MB, we have 3 clients. If we want to do a classical centralized machine learning, we need to transfer these 200 gigs to a central location and train our model. But if we would like to go with the federated machine learning kind of approach, this is the kind of one round based communication overhead that we can expect. Oh, fairly okay. And here the idea is that 3 clients and model size that goes on the wire. And if, let's say, we need 100 rounds to train our model, in the end of the day, for based on 100 rounds, it will be around 3% of the data that will go on the wire. And that's not the raw data. That will be the model. That was the quickest possible, I think, introduction that I would like to just give you to highlight why we get really excited about federated machine learning. So in around, I think, right after the first article in 2016, when about federated machine learning, we started to look this whole thing very closely and especially my interest was more towards like, okay, it has all the essential components that can unlock many use cases. It has the distributed infrastructure side, it has a machine learning side, privacy preserving aspect, communication efficiency. So that is definitely very interesting. And our first approach towards federated machine learning was that, okay, this is very interesting. How can we build more reliable, scalable, federated machine learning frameworks that can address challenges related to both cross silo and cross device settings? So we started to develop a framework FedN. It was, yeah, I think in 20, yeah, 20, I think around 2018 or yeah, 2018, 19, we started to have the first architecture. I will not go into the detail of this framework at this stage because there is a full talk available from the same platform Flow, where my colleague Andreas have actually explained that very well. And but the overall idea is that with this kind of framework, we would like to build production grade systems. And when we published our first article, it seems like we can really make a bit of an impression on both in academic side but also in the industrial side when we started to discuss more and more these kind of possibilities. And based on the initial article and also our work in that direction, we thought that okay, it's time to start a more serious effort towards commercialization, and we started this scale out system, a spin-off from Uppsala University. And currently, we have built a production grade system for commercial use based on the architecture of FedN that we have presented in CC Grid conference a couple of years back. So the idea there was more like, okay, how we can help real world use cases there. So again, the focus was very much towards system heterogeneity, data heterogeneity, communication efficiency, all those aspects that allows different use cases to unlock based on federated machine learning where data cannot be shared. We knew that cybersecurity is also an important area and people are working in that area, but it was not very much in our focus at that time until we saw one of the articles that was published by Google researchers, where they have made a very interesting claim that they said that in the end of the day, if an attack requires more than 10% malicious client in federated settings, it's not a real threat to federated environment. It was a pretty, I think, big claim. We thought, and they with if you see this article, maybe some of you have already seen that. The article very nicely highlight that here are different attacks, here are different client settings, and they have shown that okay, some attacks are not really making a lot of impact until the malicious client size in the whole population size is more than 30 or 40%. And they said that the point that they made was mostly from the cross-device kind of setting side, where the idea is that, okay, if there are 1 billion devices according to them that they are handling, and if 10% are compromised, then it's still in millions. And they said that if millions of devices in a network are compromised, then it's a network problem, not a federated machine learning problem. And that actually brings quite a lot of interest that, okay, this is very interesting. How about starting a preliminary study around the idea that, okay, how we can see different attacks. So this is how we started to go more towards cybersecurity area when it comes to the federated machine learning. So we try to simply reproduce the results with the basic settings. Here you can see that we are using label flipping attack with 10% and 20% malicious clients, very vanilla settings, distribution, data distribution, balanced IID, MNIST, handwritten digit data set. And here you can see that in a very basic, simplistic settings, label flipping attack doesn't really manage to do much up to 20%. Blue line is the baseline, then green and orange are 10 and 20% malicious client. But still there is something going on in the network that is not correct. I mean, there are malicious clients. And this plot shows like, okay, things are fine, you can still continue, which is very interesting. And this is the part that they have very nicely highlighted in the article. What we saw in our preliminary results that the kind of plot that not many are very interested in, the training accuracy. While in the validation side, you can see that the impact is negligible, here you can see that you can clearly see the difference. And that makes a lot of sense because think about if you have few clients in the network that are malicious, and according to their data, based on the label flipping attack, if they think that okay, the gradient should be in this direction, and and the honest clients that are in majority says that the gradient should be in that direction. Based on very simple Fed average approach, it will go more towards the honest one. That is how you prepare the global model. In the next round, when the global model sent by the server to all the clients, the malicious client started to see that, okay, now the gradients initialization is again here. So every time a new global model comes to all the clients, malicious clients started to have a bit of a struggle. And that was very interesting for us. And we thought that, okay, this is interesting, but this is only one attack. How about other attacks? We started to look at the backdoor. Turns out like, yeah, backdoors are very strong attacks, and you don't see anything when it comes to the validation loss, accuracy, even in the training side. But when it comes to the attack side, what you can see is that this is the true labels. And here, when you introduce the backdoor on the images, everything turns out to be 6 because here you can see that I have in my training, I just said that this kind of images should be 6 with this plus sign. So even if you have 3, 4, 5, as long as you have a backdoor, things started to get problematic. And same as for when you go more towards just um, systematically exploiting the structure of the backdoor. So here we have just put the straight line because the plus sign has two lines, horizontal and vertical. And here we just put the vertical line. Still, we see that the 6 is more than what was in the original distribution. So we work further on, we try to find out different ways to run our more experiments to better understand the attacks. And we have recently launched or published this GitHub repo, where the idea is that now you can run range of different attacks with range of different aggregation schemes that can help you to better understand the impact of different attacks on different data sets, and also based on different robust strategies. That was very good. But then the question came to us that, okay, there is definitely room to actually design new aggregation schemes or robust aggregation schemes that can address the kind of challenge that we have in hand. And for us, the goal was more like, okay, how can we design aggregation scheme that does not require validation set to be centrally available, because all the clients have their data set. How can we have a centralized validation set? If we don't have, how can we really find out if there is anything going wrong in the client side? Again, robustness against attacks. There are different attacks. We can study individual attacks, but when it comes to the aggregation scheme, we would like to build something that works for different attacks. And then the most important is that we have seen that in literature, there are robust aggregation techniques that are very much towards static bounds, where you need to define like how many uh, malicious clients are there in each round, depending on the subsample that you select, which is a bit challenging in realistic use cases. And also, another important feature that we would like to have is that, okay, now we would like to design a robust aggregation scheme, but we don't want to penalize the clients that somehow have a extreme non-IID kind of settings where the gradients are a bit different than the rest of the clients. Though it seems like they are different than others, but it's not. It doesn't mean that they are malicious. So how can we build a more fair treatment towards honest clients where when the condition on the data sets are different? So fairness has very different meaning, but here the only thing that we are focusing on is like, okay, contributions need to be included in that. So based on these kind of requirements, we have recently published our article in this direction where we are using GANs to design a more robust federated machine learning approach that can handle different attack types. Now, from here onwards, what I will do is that I will present the article and the assumptions and the settings that we have so that it will be easier for us to understand the results of this article. So first of all, the problem setup. So here the threat model that we have is that, yes, we have n number of clients, and out of n, there is a subset A that is malicious, and we would like to somehow control that. Adversary goal is to either misclassify, impact the model in a bad way so that either the convergence will reduce, or in other words, it started to have a misclassification. Adversary's capabilities are more towards like, okay, it has information from either the group of malicious clients or at least the individual malicious client side. It has limited visibility according to the local settings, and may or may not, it has information about like how the aggregation scheme is working. So these are the basic settings that we have. Assumptions that we made is that the server side is not compromised. Server side is honest. Again, when it comes to the client, the adversarial clients, there might be a group of malicious clients that are attacking to this, that are trying to compromise the model. And then it's basically only the local data that is available on each client side. That is where they have the access to the data, not anywhere else. So based on this problem setup and assumptions, we have designed the defense strategy. And what we have suggested is that rather than going for anything that is more centralized in terms of validation set, which is unrealistic, how about if we started to generate a synthetic data using CGAN, the conditional GAN kind of environment, where the idea is that if we start the training process, and after a couple of rounds, we have a global model, and that global model will be used as a discriminator to generate the synthetic data on the server side. And then we use that small data set to validate or find out the contributions coming from the client side in terms of their model. So in the end of the day, clients will do exactly the same as we know from the vanilla federated machine learning setup. They have their data, they have their models. On the server side, the changes will be according to this setting, where we train a GAN and then use that GAN to generate the synthetic data. And this basically help us to filter out like if the client contributions are extremely different, or there are something that is going on that need to be well taken care of when it comes to the training setup. So how it works is basically these are the 3 steps that we need to take care of on the server side. The idea is that we use this function G to generate the samples, and then use the discriminator D for that is basically the like let's say step T or step T global model uh, that will be used to generate right kind of input parameters. And then we use this loss function to actually train our model. So in more mathematical way, this is basically the input parameters. Then we train a global this generator, and this generator generates the samples which get penalized by this D based on the labels, and then we uh, calculate the loss on it. So based on this kind of settings, we have defined our defense settings or formulation, where the idea is that this conditional GAN give us a data set that can be used to really find out that whether the incoming model is based on something that we can trust in terms of honest client side, or we can discard because clients that kind of model is not something that is coming from the honest clients. And for that, we have designed different variations of our approach. First is the fixed threshold approach, where we just define like, okay, let's say 80%. If we see 80% accuracy, the model we will accept the contribution. But that turns out to be very stiff, as I mean, it will not be easy to attain very high accuracy in the beginning. Then we move more towards adaptive one. Adaptive one means whatever contributions that you get, you just try to set that, okay, we would like to go on the upper side, or we can just take a mean or average based on that and then do the aggregation. Another variant that we have developed for this kind of client selection mechanism was based on the clustering mechanism. So architecture-wise, this is how it looks like. As I said, that the client setup is exactly the same. Clients have their local data sets, they do the training, and they submit their local models. This is the new part that basically generate this Z. Z basically used together with the labels, and then using this generator, we use our discriminator to find out like, okay, whether the sample is aligned with the labels or not. And then we use this mechanism to further filter out the client's contribution. This is basically the overall framework that we have designed. When it comes to the experimental setup, these are
Yeah.
the 4 attacks.
May I have a quick question regarding the setup? So,
Yes.
could you please remind us how you get the CGAN? How the CGAN is trained?
CGAN trained. So the assumption is that since we are using a model on the client side, and the use case is defined, so we have the labels. We assume that the labels are known. So this Y is something that we expect. So for example, let's say if we are using CIFAR10, or if we are using MNS, then we know the labels. And using that label information, we generate this Z from a distribution, and then use this model G that give us some input. But then we need to align that input or the input parameter to the actual labels. So then this global model actually tells us like, okay, whatever input you are looking at, it needs to be aligned again according to the given label.
And how exactly you train the generator?
Generator is actually, I think Osama is here. Maybe Osama, would you like to add something?
Sure. I can try to explain this. So the idea is that a global model, once aggregated from different clients, contains sufficient information about the local distributions of the clients' local data sets. Our intuition here was that, okay, we don't, because the GANs or conditional GANs assume that you have large amounts of data to train them. And most traditional GANs work by either providing like real or versus fake samples, and then the job of the discriminator is to distinguish between real samples versus fake samples, and then penalize the generator based on how well it's able to identify those. But in our design, we don't have, because this is a common limitation of federated learning, we don't have a common data set to train these GANs. So what we do instead is to use the global model as the discriminator, and then keep this discriminator part fixed to that global model at any timestamp t. And we, for the generator's input, we provide it with two parts, noise and label, pretty standard, and then feed the output from the generator to the discriminator. And if the discriminator, which is essentially the global model at this timestamp, is able to successfully identify that it belongs to class Y, then okay, we don't penalize this. But if it's not able to, then we generate a loss function based on that and try to update the parameters for G. So essentially what we are trying to do is not generate perfect samples, but generate samples that align with the current global model's decision boundaries. Yeah.
Yes, I see. And how long usually you train that, like in each step?
So this is
How many
basically,
global steps would you take for the generator?
so there
So,
are two. I can start, and then Osama, you can.
sure.
So there are two different ways to do that. First is that if, let's say, your use case is not extremely complicated, then you can use, let's say, fourth, fifth, or 10th round kind of model to get started, but it really depends on the use case to use case. So that is one known thing that you need to empirically check, that which model will be something that you can start when it comes to the training of the when it comes to the use of the discriminator. Yes. And I think there is one more angle to that, is the amount of computations that are required to train that. This also depends on, currently, if you start with a very small kind of federation, then the computational time will be high. But if you scale it up with the number of clients that you have, then you will see that it has its own computational overhead, but then it started to be a more you can say comparable. Yes, Osama, you would like to add something?
I think you have answered it appropriately, but if the question, sorry, I understood the question to be like, how many rounds do you train this GAN for to get a good enough performance for this? So from our experiments on datasets like MNIST, Fashion MNIST, and C410, at worst, we would only use like 10 epochs or something of standard batch sizes of, let's say, 128 or 512 samples per batch, with 100 batches per epoch kind of situation. So you don't need huge amounts of training to generate reasonably well. Like, not reasonably well should not be a good word to use here, because the samples are again not necessarily samples that like look like, or in visual sense look like the samples from clients' distributions, but they are somehow relevant in detecting or identifying malicious contributions from benign contributions. Yeah.
Maybe something that I'm missing, or something that's clear, not clear to me. Is it that, I mean, on the server, how is that? I mean, for GANs usually, or to train the discriminator. Oh, no, no, okay. I actually answered myself. Like, since you don't train the discriminator, you actually don't need on the server, you don't need any
Exactly.
real data. Yeah, got it.
Because
Okay.
discriminator is basically your global model after
Yeah.
a few rounds. Okay. Yeah.
Okay. Yeah, thank
So
you.
you're welcome. And from the audience, if you guys have any question? No? Okay. So now we will move more towards the experimental setup. So these are the 4 attacks that we have considered. These are the 3 data sets that we have included in our experiments together with the models mentioned here. And these are the standard aggregation schemes available in literature that one can use as a baseline to compare the kind of solution that we have. And then these are the kind of data partitions that we are using on the client side, both IID and non-IID kind of settings. So, and again, in our experiments, you will see that we are not going more towards a very high number of malicious clients. All the experiments are between 10 to 30% of malicious clients. This is mainly because our thinking is more aligned towards what Google researchers has presented. So though their number was very stiff towards less than 10, but we thought that, okay, it will be good to have a bit of a balance from 10 to 30 so that we can cover a bit more compared to what they suggested. So first of all, what we have done is that first we would like to showcase that, okay, fine, this is a nice approach that we have developed, but does it has any impact in terms of accuracy? So what you see in this table is that based on this MNIST, Fashion MNIST, Cypher 10, these are the kind of numbers that known aggregators can give you. And these are the numbers that our different variants based on the CGAN can give you. And the numbers are almost the same. So it means that when it comes to the all benign client, clean environment, if you use the kind of approach that we are proposing, it doesn't make any difference in terms of results. Then the question comes like, okay, what happened if we started to add attacks? So what you see here is that, again, we have these 4 attacks. As mentioned earlier, random noise, label flipping, sign flipping, and backdoor. Please note that in the backdoor, we have 2 columns. One is the accuracy that is based on the normal images that you use to do the predictions. And then we add backdoor in those validation data sets. And that is attack success rate is basically what happened when you add a backdoor in your validation. Does it started to misclassify or not? So this is basically the 2 important things. And that you can see when we have 10% malicious client, 20% and 30%. And we have done that for all different data sets that we have considered. Sorry, these numbers are way too much for one slide. So let's go step by step. So if you see, when it comes to the 10% malicious client, let's take this multi-crumb. You can see these numbers that are what crumb can give. And then you can also see what kind of accuracy you can get from backdoor from crumb when it comes to the backdoor, and then at the same time what kind of attack success rate is there. So here you can see that our numbers are not different than or comparable to the other methods, but at the same time attack success rate is extremely low. In first 2 options, yes, they are high, but when it comes to the adaptive methods that we are proposing, attack success rate is very low. But here the idea is that it's 10% malicious clients that we are talking about. If we go towards Fashion MNS, you will see that, yeah, sure, things are not bad. They are comparable. But at the same time, when it comes to the attack success rate in backdoor attacks, our results are better. And same for the Cypher 10 as well. But as you know that when it comes to the more challenging scenarios where, let's say, you have 30% malicious clients, you can clearly see that our methods compared to the already known aggregation approaches also suffers. with the high attacks, high attack success rate. So as long as it is, but I mean, yeah, so that's the kind of comparison I would like to highlight. So when it comes to the limited number of malicious clients, sure, things can be better handled, but when it comes to the high malicious client rates in the federation, sure, all the known methods suffers significantly. But then it comes to the adaptive behavior that I have highlighted. So here what you can see is that these on the x-axis we have number of rounds, and on the y-axis we have clients. And here you can see that in each column I have honest clients with green, and then I have a different number of malicious clients in different rounds. And then the challenge is that, okay, if we have this kind of adaptive behavior from the malicious client side, how our method or our proposed methods work compared to the well-known aggregation methods. So here you can see three approaches from us that we are comparing with multi-crumb. And what we are seeing here is that according to the color scheme that we are presenting, true positive means like you have benign, and actually the actual label is, or actual client behavior is benign, and it is predicted as benign, true positive. Red is when it's malicious and it is predicted as malicious. The more challenging, or what should not happen, is this: when the client is actually malicious and it turns out to be benign. And here you can see that with the known approaches, there is a bit of a challenge when it comes to the this malicious client environment. But on the other hand, you can also see that when it comes to our approaches, there are false positive. Means like there are some honest clients that where the contributions should be accepted, but the system decided, or the approach decided, not to include their contributions. When it comes to the adaptive mixed one approach that is based on the mean, you can see there is quite a lot of false positive here. But when it comes to the fixed threshold, or even the median kind of thing, that is quite different. This is basically based on the MNS with 30% client. And you can see the similar kind of behavior in CIFAR 10 dataset as well. And in the article, we have also included more results related to that. This is another view of like how the attacks look like over the time. And Samuel, your question about like how many rounds will be good to initiate this GAN-based kind of approach. So here K is basically the number of initial rounds that you complete, and then the attack started. So here you can see that, sure, the more rounds, honest rounds that you can avail, the better GAN will start it to detect in terms of malicious client. This is basically all the results that I would like to highlight quickly. I would like to also highlight one current directions that we are thinking more closely to further continue our research is, sure, we can select the synthetic data, but where those data points should be and how we can select a synthetic data that is a good representation of the boundary. So for example, do I have all the data points that are far away from the boundaries, or we have a good mix and match where some points are close to the boundaries, some are the others? With current synthetic data that we are generating, this is the kind of thing that is currently not very well captured. Second is that where should the model attestation should happen? On the server side, because then maybe the client can say that, okay, my contributions were honest, but you just discarded that because of XYZ reason, because whatever is happening on the server is also unknown to the clients. So where should this attestation or the authentication of the clients and models should happen, and what kind of effect it will bring? One last thing that I would also like to highlight overall in terms of direction is that this is something that we all are familiar. This is standard federated machine learning. In the end of the day, when we train our machine learning model, we either have this flat minima or very sharp minima. So what can we say about this global model when it comes to the federated machine learning kind of settings, and especially on the when the data is on the client side? So this is basically overall direction that we would like to further do our research, not related to very much to cybersecurity area, but overall. So what we would like to do more is going more towards this sharpness aware minimization, just based on the model that we prepare, how we can do that. It has quite a lot of interesting characteristics, and also it can help a lot when it comes to the non-IID client distributions. So this is all what I would like to cover, both from the cybersecurity side and a little bit from the overall federated machine learning side. If you have any questions, I will be happy to answer.
Please, if you have any questions, then just feel free to unmute yourself and ask a question, or just post it to the chat, and then I can ask it for you.
Hi, can I ask something?
Yes.
First of all, thanks for your talk. It's very interesting, especially for people who don't work precisely into security and for the learning. I have some questions about the results you showed in the tables. Yeah, exactly. Would like to ask, what is the difference with the adaptive variants of your method? Because I see a lot of difference comes with the backdoor attacks in the attack success rate. And why do you think this performance gets much lower when you, for example, test on Cypher, even with the low attack rate?
So basically, overall, I guess if you have worked with the backdoor attacks, they are very challenging. So the first example that I showed you earlier, when we were not considering this kind of approach, they are not very easy to detect. So what you can see is that with even 10% of the malicious client, the attack success ratio is pretty high. And it's not like easy to detect like what kind of approaches can further help in terms of finding out whether there is a backdoor or not. So it's overall very hard in that sense. But maybe I didn't get your question clearly. So if you can repeat.
Yeah, my doubt was, what is your intuition behind the fact that, for example, with MIST, the adaptive variance practically reduced to zero the attack success rate, while with, for example, Cypher, still gets pretty high, and it's probably the model or the tag set.
Well, I think I don't think model is a major challenge here. It's more like MNIST is a small data set and has a very like only 10 classes with very, you can say, a clean kind of data set that is easy to learn and work with. But when you started to go more towards complex data sets like Cypher 10 or 100 or further with more data points and distributions, then things started to become more challenging. But maybe, Osama, would you like to add something?
So like you said, there are two dimensions to this question. The major differences between the MNIST and CIFAR10, of course, is the complexity of the dataset or the dimensionality of the dataset itself. And the other dimension, like Ricardo, you identified correctly, is also the model that we use to train on these datasets. So let's say for MNIST, we use a simple convolutional two-layer network, which is not so complex. But for CIFAR10, we, for example, use ResNet 18 model, which is a very deep model and has about 10 million or so parameters, if I remember correctly. Hence, it's more challenging to to carry out backdoor attacks or to hide your backdoor attacks in this kind of setting. So it's more a bit of both the complexity of the data set itself as well as the challenging aspect of the model that we use. And a general comment here would be that backdoor attacks are, generally speaking, quite complex for all robust aggregation or the secure federated machine learning. These have been a pain for quite some time, and we still haven't figured these out completely. Because if you look at them, realistically speaking, all these, and including our approach, this is not a critique of other variants, but it's a general critique of all secure methods or secure aggregation methods, that we rely on some kind of detection so that we can detect some kind of anomalies in accuracy or something like that. But the objective of backdoors is to maintain high enough accuracy while injecting some ulterior motive into the trained model. So it becomes really challenging to detect them, and probably it's best to rethink how we want to proceed in this field in order to be able to tackle these kind of challenges.
And that's why we have this two columns, especially for backdoor. One is the accuracy, where all the images are clean, but then attack success rate is the one where we have included the images with backdoor.
Thanks for your answer.
You're welcome.
Any other questions, the audience? Let me ask one. For your what we can call aggregator, have you considered maybe doing theory, for instance, like showcasing that as is like kind of common in Byzantine robust data literature, to actually show that this is this robust aggregator, meaning that it's like it can actually provably come close to the true mean, or like because I think it's kind of interesting, like what you would need to assume, or what you would need to show for your gun that would actually show that, okay, this is the right thing that just gives you that discrimination that you need.
Yeah. No, I think no. Right now, so far, what we have done is more like, first we would like to empirically show that, okay, this is something that is doable, and it achieves the kind of accuracy level and the stability that we would like to have. So theoretical bounds are still missing that need to be further studied.
And okay, so maybe one second question. So you said at the end that you would be interested in looking into more towards like a sharpness in the federated learning. Is your main motivation like the same as in like a centralized learning, where you're trying to get like more flat minima to get better generalization, or is it that you also expect that it would have some better properties, maybe in terms of like a robustness, and maybe it's going to be less less sensitive, let's say, to the backdoor attacks? So
No,
where is the motivation?
So the motivation is more towards generalization and robustness. So here Actually, one of the challenges that we see quite a lot is that when it comes to the non-IID conditions, and especially the client contributions are not very well representative. The approach that normally we have is that, okay, start a round for all the clients. But what if some clients need more rounds than the others? And that may have some effect. But how do we know that whether from the client contribution side, we are somewhere in the local model that is representing a better flat minima than some clients that have a bit more sharp minima. And if we blindly continuously doing the aggregation on that, sure, in the end of the day, we have seen that Fed average give us a decent estimate and we have the model. But without having access to the data, giving any kind of, you can say, estimate in terms of like how the loss landscape look like is very difficult. So for example, one simplistic approach that we have tried in our basic settings is the path norm. So the path norm, when the rate of change of path norm started to get flat, then you can really see that, okay, now maybe there is not much to learn from the client side, but this is not true for all the clients. Maybe one client have that kind of flat minima representation. So all these things are something that we would like to further explore, both for the robustness and generalization, but not in terms of the cybersecurity. It's more like preparing better, stronger, and accurate models.
Thank you very much. And if there are no other questions, thanks again for a great talk, Salman, and thanks everybody for tuning in today. And hope to see you in the next seminar. Thanks again. Please, Salman, if you can share with me your slides, I'll be posting them with the recording soon. Thank you very much once again, and for all, have a great rest of the day. Bye.
Thank you very much for inviting me. And if you guys have any questions or anything, feel free to contact me via email address. Otherwise, we have this LinkedIn channel. You can feel free to connect me through that. Thank you.
Thank you.